Okay, so thank you very much. So next we have another contributed talk by Yukio Sato, who's going to speak to us about in situ electrical biasing at the nano and atomic scale.
Thank you very much for introduction. My name is Yukio Sato from Kyushu University, Japan. I'm going to talk about our in situ TEM study, and more recently, we are trying some atomic scale in situ study for ferroelectric and dielectrics. And because this is my first time to come to this conference, I'm going to talk about a little bit early data we have published several years ago. And also, in the last half, I'm going to talk about our recent studies on in situ stem observation of dielectric and ferroelectric crystal at high precision. So probably I don't talk much about this already because many of you already know about this crystal very much. So PMN PT crystal is a solution of PMN and PT with having perovskite crystal structures, and for the so-called MPB composition, this material exhibits very high piezoelectric constant. And because of this excellent piezoelectricity, this material is used for medical imaging devices. And in terms of its crystal structure, it has been reported that the monoclinic phase exists in the MPB compositions. On the other hand, in terms of its domain structure, it has been reported that ferroelectric domains scale down to nanometer level. As you can see here, in the case of MPB, PMN, PT, the width of the ferroelectric domain is roughly about 10 nanometer or so. So then the important question should be, how does this ferroelectric nanodomain respond when external electric field is applied? And I believe that prior to our study, the response of nanodomain had not been observed in real time. So in order to visualize that, we have used I'm sorry for that. We have used electrical biasing in situ TEM. As you can see here, in this method, we can apply external electric field to the sample while observing the specimen with TEM. And for this purpose, we have used commercially available TEM holder, and we have designed special test fixture for this purpose. And by using this method, we can observe the internal structure of material with high spatial resolution at the nanometer scale at this experiment. And also we can do this observation in real time. In this particular experiment, the temporal resolution was 1/3 second. And then let's move on to the results. This image shows that the domain structure right before we apply the electric field, and its domain structure schematic is shown here. In this field of view, there are 3 different microdomain bands, and each microdomain is composed of training of lamella-like nanodomains. And for this sample, we applied electric field, and the movie starts here. And now the electric field is off, and now it is turned on. Then right after when the electric field is turned on, the domain structure changes, and after it is removed, that it comes back to nearly back to the original state. And this kind of response can be repeatedly observed on the apply and release and the electric field again and again and again. And this is a domain structure during the electric field is applied, and the domain structure changes from this state to that state. And when the electric field is released, this domain state nearly comes back to the original state. So what we find is that the change of structure is the dominant process of the structure change is a domain reorientation of the domain. And also another important thing should be that even after high electric field of this much, the high density of domain will still exist like this. And we also found that the domain structure is reversible on the applying and release of the electric field. And we have repeated this experiment for the different biasing directions. The top half is for the electric field along 100 direction, and the bottom half is for the 111 directions. And we have again observed very similar results. So before biasing the electric field, the domain structure is like this and like that. And when it is applied, the domain structure changes nearly in a single microdomain band. However, the high density of nanoscale domain will still exist. And when the electric field is released, the domain structure nearly comes back to the original state. So we found that commonly to the different biasing directions, we have observed similar behavior of domain structure changes. And after we published this paper, I have got many questions many times about its crystal structure of our sample, because after these studies, first of all, because this material possesses this sort of very tiny domain structure, so this situation complicates the understanding of crystal structure at the single domain levels. So then after this study, the number of reports has been published for the crystal structure investigation, and different papers reported different conclusions. So we decided to study the crystal phase of our sample by ourselves with our method. So for that purpose, we have used electron diffraction analysis in TEM. So here's some experimental detail, but because of the time limitation, let me skip most of this. However, one of the things that I emphasize here is that we have measured electron diffraction pattern very carefully, like this. This is one example of the observed pattern, and then the distance. The individual diffraction spot was analyzed very carefully, particularly the distance from the origin, 000 spot, was carefully analyzed using the Gaussian fitting, because the distance from the origin is inversely proportional d-spacing, so we can analyze d-spacing for the individual diffraction spots very carefully. And then, so this is a field of view that we have investigated electron diffraction from this sample. And in this field of view, there are two different microdomain bands, A and B, and each microdomain band is composed of the chaining of and lamella-like nanodomains with two different orientations. So if we zoom up this area, here are two different microdomain bands, and each composes of two different nanodomains of two different orientations. So if we choose this round area for the electron diffraction, we can investigate the diffraction spot for electron diffraction for the nanodomains of four different orientations. And here's the result. This is an example of the observed diffraction spot for 2 bar to 0 spot. And by our careful analysis, we have found that there are four individual diffraction spots for this 2 bar to 0 spot. And then if we carefully analyze the distance from the center, from the origin, we have obtained that there are four different d-spacing for these four spots. So point is, how can we analyze this result? And then the point is, if the crystal structure is cubic phase, the 2 to 0 plane should have one identical d-spacing, so this shouldn't have four different d-spacings. Similarly, if the T phases for the R phases, they can have only two different d-spacings. So this result indicates that this result cannot be explained neither by T phases nor R phases. So it may be indicated that the crystal structure is of lower symmetric phases, such as monoclinic phase. So after based on our finding that our domain response and crystal phase analysis, we try to estimate the domain effect to the piezoelectricities. Here we very simply assume that without electric field, the specimen is equally divided into 1/3 for C-axis, B-axis, A-axis, parallel to the 001 direction, and when the electric field is applied, for all entire the region becomes C-axis parallel to 001. Using this very simple assumption and reported lattice constant for monoclinic phases, we found that domain effect can be up to roughly 0.2%. And we have also found that the domain response is reversible. This explains experimentally reported low hysteresis curve. So we think that domain effects may not be negligibly small, and this also explains low hysteresis in the field strain curve. And after we reported this sort of study, I got this sort of question or comment many times. Because the TM is in principle have a very high spatial resolution, why don't you carry out in-situ study at atomic scale? So we have tried this sort of experiments, and then so because of time, let me skip this movie, but my conclusion is that direct response cannot be observed at atomic scale. However, if we keep applying electric field for a long time, everything is stable, so we can observe atomic scale structure under electric field. So we have tried to evaluate how much we can measure the atomic position precisely under the electric field in this sort of in situ STEM experiment. And first, we have checked the precision of lattice constant measurement. And this is a measured STEM images under this much of electric field, and then this side is a result. For the first scan direction along this direction, we obtained the precision of about 4 picometers. On the other hand, along the slow scan direction in this way, it becomes slightly worse at 7 picometers. So we found that the precision of at 7 picometers can be achieved. And similarly, we have observed, we can measure the position of titanium ion at 5 picometer accuracies. So we are currently applying this method to ferroelectric material, and here is the result, ranging from plus 40 kilovolt per centimeter down to minus 30 kilovolt per centimeter, and these results are currently under analysis. Thank you very much.
Thank you very much. We have time for a few questions. I'll start with a question, actually. So you showed images under a static electric field. If you're changing the electric field while you're measuring, does that induce any kind of instability in your imaging, or is it only, I mean, it's one thing to show it under static, but can you be varying the field and taking a picture at the same time, or is that more difficult to capture?
You mean for this result?
Yes.
This is, how can I say? This is step by step. Mm-hmm. So I applied this much, wait for minutes or 10 minutes or so, and then take images and stop it, and apply this much, wait for a while, and take it.
Okay.
Repeat these sort of things, yes.
Okay.
Yeah, it's a beautiful work, very useful for the community. I wonder whether you ever tried or thought about looking at thin films of PM and PT.
Not have thin film sample.
How thick was the sample you look in transmission?
It roughly 100 to 200 nanometer.
So in the PMNPT, do you see any chemical heterogeneity?
I have observed the formation of chemical order domain. It's very small, a few nanometer in size. Except for that, I haven't observed any chemical.
Okay, but do you see any then correlation in the polarization in the chemical order?
I don't know. I have no idea. Thank you very much.
And we'll take one more question while our next speaker comes up, please.
So for those nanodomains, are they in monoclinic phase or in a mixture of ramifido and tetrahedral phase, based on your studies?
Because our study can measure only a very narrow region. So even in a narrow region, I believe that it's a single monoclinic phase. However, if you think about wider region, our study cannot tell everything.
Thank you again.
Thank you very much.
Sorry.